Today's lesson's on the conservation of momentum. One of the great conservation laws in all of physics, very similar to the conservation of energy. Basically, it says what we start with is what we end with. So the book gave you an example of two billiard balls colliding. Based upon the data, how did the gain in momentum of ball B compare to the loss in momentum of ball A? Let's cut to the chase here. If you look before the collision, that's this set of data. The only thing moving was ball A, and it was moving at 4.5 meters per second. Its total momentum, 0.72 kilogram meters per second. That's just done by multiplying these two numbers together. The ball B was not moving at all, so it had no momentum to begin with. Well, after the collision, we see that ball A is continuing to move 0.1 meters per second, so it's got a little bit of velocity up here. Ball B is certainly moving a lot faster, 4.39 meters per second. But overall, what we see is that the total momentum, if I add those things together, I started with 0.72 kilogram meters per second of momentum, and afterwards I've got about 0.72 kilogram meters per second of momentum. Amazing stuff. The total momentum stays the same during this collision. Now it's off a little bit. That's maybe some of you looked at that and said that's 0.718. Well, in reality, there's not much difference between 0.72 and 0.718. And so that we see experiments show that the total momentum is a conserved quantity in these collisions. So experiments show that the gain in momentum of one object exactly equals the loss in momentum of the other. So what we start with is what we end with. If this one lost about 0.7 kilogram meters per second, this one gained 0.7 kilogram meters per second. Let's move on. Okay, this can be quantified with an equation.
Change in momentum of object A, how does it compare to the change in momentum of object B? Well, we should see that that is in fact an equality, that one object changes its momentum by the exact same amount as the other object but in the opposite direction. Another way to write that is that both objects, when I add up the change in momentum of each object, it adds up to a 0, which means the total momentum stays the same. Whatever one object changes its momentum by, the other changes by an equal amount in the opposite direction, and we get no overall change. Now this leads to a very wonderful relationship. Just says that the initial momentum of a system beforehand, the sum of the initial momentum of every object that's part of that system, is equal to the sum of the total momentum of every object after that system, or after that collision. They have to be equal to each other. Now it can be written with this relationship here. We don't always have all of these variables that we're going to end up using, but this is the way that we would write this if we had two objects that are moving. M1 V1 initial plus M2 V2 initial goes to M1 V1 final plus M2 V2 final. Looks really confusing. That's why we're going to look at many examples today to help you with utilizing that relationship. So when is conservation of momentum applicable? When is it practical? Well, we started our whole discussion here with looking at football players, and I said, what's the determining factors that will make this person either score a touchdown or that person keep them from scoring a touchdown? We talked about their mass, their velocity, but ultimately because they can push on the ground. It's not just their mass and their velocity, it's how much force they can exert on each other because of the frictional force that's acting. The person's legs come into play here. How strong are they? Over here, heck, the only things that determine which way they're going to move during that collision is how much mass and how much velocity they have. So we can use conservation of momentum always. It is always an applicable law, but it's not always practical. Whether or not we use it depends on whether or not we can isolate the system. So let's first just state this up here. Conservation of momentum is always applicable. We can always use it, but it's not always practical. We have to have a system that can be defined as closed and isolated. Now, closed means that there's no mass that enters or leaves the system. We have to have a system of objects that keep the same amount of mass. So we can't have mass leave or enter. We also can't have any outside forces that exist. So they would be forces that are existed outside of the system. The problem with using conservation of momentum here is that there's outside forces, the forces that the players exert on the ground. And so we wouldn't have a good way of defining a system that includes all internal forces. We'd have to include the earth or the football field as part of that system, which doesn't make practical sense. Here, the forces are all internal. And so when the one person pushes on that person, they push back with an equal amount of force in the opposite direction. They have to by Newton's third law, which essentially has only internal forces that are acting. Now there is gravity acting on here as well, but those gravitational forces act downward for both of these, and since momentum is a vector, it makes sense. We could actually use conservation of momentum to analyze this, but not so much for that. Now we have some other examples that we can look at. Let's look at this one here. This is a fairly boring example of conservation of momentum. We have a bunch of gas particles inside of a cylinder, and they're bouncing off each other, colliding all around. And even though there's lots of complex interactions going on here, the total momentum stays constant because they're all internal forces. So it is isolated, and it is closed. And so we could say that the total momentum stays constant. And sure enough, it'd make a lot more sense if I could actually show you that in real time. So let's go ahead and see if I can't show you a picture of that going on. And I have that hidden right there. There it is. All right, so here we have, this is from Wikipedia. This is talking about elastic collision, but nonetheless, this is just a picture of a bunch of particles that are interacting with each other. They could be gas particles, but they're bouncing off each other, colliding with each other. And what we see is that the total momentum stays a constant there for every change in momentum of one object. It corresponds to another change in momentum by another object that have to exactly balance each other out. Now, we could also use conservation of momentum to describe this kind of interaction. Here I have a person jumping off of the Earth, not drawn to scale, thank you. But as that person jumps off the Earth, we have an isolated and we have a closed system, which essentially means the total mass stays the same and all forces are internal. This person acquires an upward momentum, P of the person, that's upward. And the Earth acquires a downward momentum, P of the Earth. And those two things must be exactly the same. The total momentum of the person must equal the total momentum of the Earth. Now, certainly, since the person has such a small mass, his velocity is going to be much greater than the mass of the Earth times its velocity. The velocity of the Earth is going to be really small in comparison to the velocity of the person. Should make sense. We don't notice the Earth recoil downward because it's got such a large mass. Now, if we took every person, if we had all 7 billion people on the Earth all get in one spot and jump in one direction, the Earth might recoil in the opposite direction with a little bit of motion. I think they've actually done that kind of, or at least analyzed what that experiment or what that would look like. They haven't really done it, but they show that the Earth really wouldn't change its motion hardly at all, just because of the extreme size of that Earth. Now, there's some other examples that we could look at. I'm not going to spend a lot of time looking at these things conceptually. I want to get into those problems with you. But down here we have car collisions. Car collisions, this is obviously an extreme example, but car collisions can be used, or we can use the conservation of momentum rather to analyze car collisions. This is one that's showing collisions. You can see some airbag deployment in there, and some, these are test dummies, if you will, for a simulated car crash. Conservation of momentum is used to describe collisions all the time, and we'll look at some of those examples as well. Now, we have some typical conservation of momentum scenarios. This helps us write the equations that describe the relationships between momentum before and after. Hit and stick, that's my term. Hit and rebound, that's my term. Explosions, you've heard of that before. These are not talked about in the book, but these are 3 common conservation of momentum scenarios. So again, we're going to show you how this equation can be written for each one of these things here. Let's look at hit and stick first. Common example of hit and stick would be 2 football players that hit and stick together. What that means is that one object collides with another object, so let's call them object A and object B. Let's just, for simplicity's sake, say that object A is the only thing moving. So let's say that's VA to begin with. VB is at rest, or B is at rest, so he has no velocity to begin with. When they hit and they exert forces on each other, and because they've stuck together, we're going to say that both objects move with some common velocity afterwards. So let's just call that V final. If I wanted to write the equation to describe the momentum before and after, I would start with this. P initial is equal to P final. The only thing moving to begin with is the first object, so MA, VA initial. The only afterwards, what we have are 2 objects that are moving. Now they have combined their masses, so I'm going to add them together, MA plus MB, and multiply that by some common velocity to get the equation for the final momentum. Both objects combined, multiplied by their velocity, would represent the final momentum. Now, in a situation like this, I'd probably be looking to find the final velocity, but I could really, once I write this equation, I could solve for any one of those variables, knowing the others, and so that would be how I'd write that equation. Now, I have another situation where I have maybe a what's called a hit and rebound. Now I have a billiard ball coming in, striking another ball, and they don't stay connected. They don't usually do that. If you've ever played billiards before, you know that. We have object A moving, and object B, let's say it's at rest. It doesn't need to be. It could be moving as well. But we're going to make it a simplified case here and say it's only object A that's moving. Once they hit, they don't stay connected. So they hit, and they rebound off each other. Now, object A could continue moving to the right, while object B would certainly be moving to the right after that collision. Object A could stop and not move at all after the collision, object B would then be moving with even greater velocity, and we can show you how we can calculate that here in a little bit. And object A could also actually rebound and go in the opposite direction. Well, in that case, what do you think? Would object B be moving faster? In any of these, would it have the greater velocity in this particular example? And the answer is absolutely. It would be moving that way with a much greater velocity because momentum is a vector. If this thing rebounds the other way, sure enough, that's going to be moving that way a lot faster. How I would write that equation, or how we would set that relationship up to begin with, is I would say something along these lines. And I'm going to need a moment to get the right screen up here. Here we go. All right. I would write MA VA initial goes to, this is the initial momentum, goes to MA VA final plus MB VB final. I have two terms here because they're moving separately afterwards. In contrast to this example over here, I only had one term because they were moving with a combined velocity. Now I have to have two terms because each object is moving separately. Again, knowing five of these values would allow me to determine the other one. And so ultimately then it becomes a little bit of an algebra game to figure out what that other variable is. And then last example that we'd look at is this example about explosions. Now this one is common when objects are combined to begin with, and then they separate during some sort of interaction. So we can have object A and object B. They push off each other, and when they do, object A recoils this way, object B recoils that way. And what we see, more than likely, since the total momentum was probably zero to begin with, not necessarily zero, but more than likely it started at rest. Afterwards, we should see that the final momentum is also zero, which means MA VA final must equal the negative of MB VB final. And again, just in case you can't see that here, that's what we should end up getting. Typically, that would be the way that we would set up an explosion equation. Now, I'm going to show you examples for every one of these things. Let's keep going here. This one is a great qualitative or conceptual example. A firecracker is placed inside of an object, causing it to explode. Don't try this at home, but you've probably seen videos of something like this. Will cause it to explode and fragment into pieces. What is the sum of the initial momentum? It would be zero, since everything's at rest to begin with. Well, what is the momentum of all of the objects afterwards? It is zero. And how I know that is that momentum is conserved in this situation. Every one of these fragments has momentum in different directions. But when I add them all up, what I get, as you recall, with vectors, when you add them, you might have momentum going in all directions with things. But when I add them, I get right back to the beginning because the total momentum must be conserved. Now, another example of that is during billiards, also known as pool. When they shoot the cue ball in for the initial break, the only thing that's moving here to begin with is the cue ball that has a certain amount of momentum. Afterwards, when the balls all scatter in random directions, what I see when I get all of these things added together, moving in all of these different directions, I should get the initial momentum of the system. So whatever I start with is what I end with. And again, no matter how complicated those interactions are, what I see is that P initial is equal to P final. Now here I have some videos that I'd like to be able to show you. Okay, so here's my first one, just a slow motion shot of a break. Here it is, a ball coming in, cue ball coming in and hitting the rack of balls there, and they all spread in random directions. We're going to watch it one more time here. The total momentum to begin with was just due to the cue ball that was moving. Let's try that one more time. The total momentum was just due to the cue ball that was moving, and then while it hit, it caused all those balls to move off in all of these seemingly random directions. If I add up the total momentum before and afterwards, what I get is the exact same thing as the cue ball coming in. I'll give you a hint. There is a question on a quiz coming up that has something to do with cue balls breaking a rack of 15 balls, and what is the total momentum of the system. You should be able to answer that. It's equal to the momentum of the cue ball coming in. Now, I guess I'll show you this one too with just a ball coming in with just a single hit. Here's a cue ball coming in and hitting the 9 ball, and there's a good transfer of momentum going on, and that's a little bit simpler than the other example. Let's go ahead and show you a couple more here. Here is a firework exploding. These are always fun to watch. We got the 4th of July coming up in a couple of months, and just be careful with fireworks, but here's a slow motion video of various fireworks exploding, and there's a couple interesting ones I really like with showing the three-dimensional nature of vector explosions. So, plus it's always fun just to watch slow motion videos. Okay, coming up here is a nice three-dimensional explosion, which I think illustrates the idea of P initial is equal to P final quite well. There it is. Nice explosion. Shrapnel going in all directions, but since the initial momentum was zero, if we add up all of those things together, we should get zero. P initial is equal to P final. All right, and last one I want to show you is just a, since football is one of my favorite sports to watch and play. Here's an example of a goal line stance. This is back in the 90s, I think, but two teams here, and I guess this was called the greatest goal line stance of all time. The Philadelphia Eagles here apparently stopped, was at the Cardinals numerous times, and there's a couple of good explosions here, or I'm sorry, collisions here that really show how momentum is a key factor in determining whether or not this person scores. So can't acquire a whole lot of momentum there. The quarterback sneak. Here he is diving, trying to dive over the goal line. Sure enough, did not have enough momentum to push back the linebackers there. Here's another example. Hits, collides, cannot make it through, just not enough momentum. All of those were isolated cases. Here's one where he's not isolated. He's able to push on the ground, but sure enough, he still doesn't have enough momentum, nor can he do enough work to be able to score. So they ended up holding them, and that's it's recognized as being one of the greatest goal line stances. I'm going to go ahead and stop it there, and let's head on back to our slides. All right, now here we have the time for us to practice actually solving some problems using conservation of momentum. Now, you have this in front of you as well. I want to go through and just show you how to write the equations necessary to be able to solve these problems. So we have a moving train car collides with another train car that's at rest. I gave you some data here, just masses. I gave you some velocities. You can see that car B is not moving to begin with. Car A is moving at 24 meters per second. That's a pretty good speed. And we want to determine how fast do the train cars move when they collide. So this is a hit and stick. My words, not the book words. We will talk about those different kind of way of describing those in section 6.3, but for right now, hit and stick makes sense. How I write that is P initial is equal to P final. In the beginning, the only thing moving is car A, so I'm going to call that MAVA initial. The only thing that's moving. Car B is at rest, so I'm not even going to write it. I could write plus MBVB initial, but that's 0, so why write it? Now afterwards, they stick together, so their masses combine, MA plus MB as one combined mass times V final. Now I'm looking for what that speed is, that V final, so it becomes relatively easy for me just to divide both sides by MA plus MB. So MAVA initial is the numerator. In the denominator, I have the sum of those two masses, and that would be V final. Now I'm not going to bother writing all those numbers in here for this example. It's just a quick computation. And when I do, I'm going to pause it here for just a moment so that I think I'm going to pause it. Where is my... Okay, there it is. It still is going. Let me pause that for just 1 second. Okay, so the numerator is 364,800 kilogram meters per second. That's the total momentum of car A. And when I divide that by the combined mass, 15,200 plus 13,700, that combined mass is 28,900 kilograms. And I see that value is about 12.6 meters per second in the rightward direction or in the east direction. So that would be the combined velocity of those two cars. Again, much slower speed, but that's because there's much more mass that's moving. Now here's an example. What if they don't stick together? What if instead they do not remain connected and train A is observed to move at 3 meters per second to the right after the collision? Determine the speed of train B. Well, this is a hit and rebound. So the equation becomes a little bit harder to write because we have two terms, or two objects that are moving after the collision. So I'm going to still start it with the total momentum to begin with is equal to the total momentum afterwards. I still only have one object moving in the beginning. That's MAVA initial. But afterwards, I have two objects moving. So I have to write that set of objects, write the variables for each object separately. So I'm going to write MAVA final plus MBVB final. And what I'm looking for here is VB final. So I'm looking for that term. Well, once I get that basic equation written, I'm going to go ahead and just do some algebra to be able to write that solution out. MAVA final, subtracted that from both sides, is MBVB final. If I divide both sides by MB, I have a way now of calculating out VB final. It's just a ratio of MAVA initial minus MAVA final all over MB. And again, when you go through and do that calculation, I'm going to save you a little bit of time here. You should get 23.3 meters per second. Let me check that. And yes, that is what that value turns out to be, so about 23.3 meters per second. Different speed for VB final here than it was here, largely because they did not move together at the end. Here, both of them were moving at 12.6 meters per second. Here, only B was moving at that speed. The other one, train A, was moving at 3 meters per second. But when I add them all together, what I get is total momentum stays the same before and after. Let's do a couple more. Here we have a 4.5 kilogram rifle that's shooting a 95 gram bullet. I'm going to go ahead and draw that with the bullet. Here's the gun inside. Here's the bullet. The gun with the bullet inside of that. The total momentum to begin with was 0. And so after the explosion, we see that the gun is going to recoil this way with a certain velocity while the bullet is being shot out this way with a much greater velocity. It should make sense that that's the case because it's so small, 450 meters per second. And what we want to do is determine the velocity of that gun after the explosion. So this would be a conservation of momentum problem. Well, since P initial is equal to 0, P final must be equal to 0. Well, that just means that whatever the momentum is of the gun, so mass of the gun, V of the gun final, must equal the negative of the momentum of the bullet. So mass of the bullet, velocity of the bullet final. They must be equal but opposite momentum. Well, the velocity of the gun then is just, let's do that, negative 0.095 kilograms. Be careful about the mass being 95 grams. It should be written in kilograms. I'm going to multiply that by 450 meters per second. And when I divide that by the mass of the gun, 4.5 kilograms, that's why I needed to have the mass of the bullet in kilograms so that those reduced. And what I would get then for the velocity of the gun is about negative 9.5 meters per second. Negative just means it's recoiling. That's the negative direction. But notice the difference in its velocity. 9.5 instead of 450. It's going to give you quite a kick there because of the velocity and momentum of that bullet. But it's not moving nearly as fast as that bullet because it had much greater mass. It also has much different kinetic energy. We went through an example like that earlier to talk about the difference in kinetic energy when you have greatly different speeds and masses. Last one I want to look at for you, 95 kilogram fullback leaps into the air at the goal line at a horizontal speed of 4.5 meters per second, collides with 2 linebackers, each of them moving with different speeds. Looks like a really complicated problem. It's not too bad. I'm going to draw this as a fullback moving this way. I have 2 objects here, linebacker 1, linebacker 2, that are both moving this way at slower speeds. What we want to do is determine whether or not the fullback scores. So it's a simple conservation of momentum problem. Now this is a hit and stick. So what I'm going to do is I'm going to start writing that equation with the traditional hit and stick setup here. But here I have 3 objects that are moving all separately to begin with. So I'm going to write that as the mass of the fullback, the velocity of the fullback initial. Now I'm going to put that in with a minus mass of the linebacker, of the first linebacker, times the velocity of the first linebacker initial, minus the mass of the second linebacker, velocity of the second linebacker initial. Now those are negative because they're moving in what I call the negative direction. I'm going to say that's the positive direction. There's the goal line. So positive momentum, negative momentum, negative momentum. Does the fullback have more momentum than the 2 linebackers? If so, he scores. If not, then he won't score. What we're going to do now is we're going to determine what the final momentum is in terms of those variables. Since they've all combined, I'm going to write that as mf plus ml1 plus ml2. Those are the 2 masses that are, or the 3 masses that are combined times some final velocity. If V final is positive, he scores. If V final is negative, he doesn't score. If V final is 0, well, that's a judgment call. Depends on whether or not the line judge think he crossed that plane or not. But let's go ahead and just plug in some numbers here. We have 95. I'm going to drop units so it doesn't look so messy up here. Times 4.5. That would be the momentum of the fullback. Minus. This is 105 times 1.2. That's the momentum of the first linebacker. Minus 110 times 1.6. That's the momentum of the second linebacker. That's all equal to the total mass. I got to check that here really quick. The total mass I get is 310 kilograms, and then times some V final that we're going to compute. And we're getting so close to the end here. Let's check this. 95 times 4.5. That is 427.5 kilogram meters per second. This next one, 105 times 1.2, that is a negative 126 kilogram meters per second. And does the second linebacker have enough momentum to stop him? Let's see, 110 times 1.6, that's negative 176. It doesn't look like he does. Is equal to 310 times V final. Let's add them all up here. It looks like the total momentum is 125.5 kilogram meters per second. So it's positive. That means he's going to score a touchdown. Is equal to 310 kilograms times V final. And that final velocity would be then just 125 divided by 310 kilograms. And that turns out to be about 0.41 meters per second. It's a positive velocity. He scores a touchdown, and they win the game. All right, and now I have these 2 problems. These are called guided practice problems. That means that you get to work on those And we're going to stop the video here, give you a chance to try those problems within about 5 minutes. That should be enough time for you to be able to solve those. We're going to have you start this video back up, and you're going to see whether or not you got those answers right. So go ahead and try those, and then come back and check that in about 5 minutes once you try those problems. Go. Okay, and so now hopefully you've had a chance to try those things, and we've replayed the video, or at least started it up again. What you should get for the answer for the first one, with the person walking in the canoe, total momentum is 0 to begin with. I write those equations here as I go through all of that, and you can follow that if you need to. This will be up here while you're working on your homework, so you can look at it in more detail. But you should have gotten a negative 3.5 meters per second for the velocity of the boat afterwards, or you could write that as 3.5 meters per second towards the west. So again, using conservation of momentum for that one. For the second problem, a little bit more involved. Here the person jumps off of the dock with some unknown velocity. They land in a boat that was moving at 1.5 meters per second towards the west. Here they've combined together and moving now at 2.1 meters per second. I want to find what that velocity was that they jumped with. So I'm actually looking for an initial condition. So VP initial is what I'm looking for. This is a hit and stick, where they have combined their masses after the collision, but what I'm actually looking for is one of the initial conditions. So once I get that, I'm going to go ahead and then solve that for VP initial, and you got a lot of algebra here, but when I get down to it, I see that the person jumped initially with a velocity of 2.3 meters per second, and that would have been in the westward direction, so that when they jumped into that boat, they end up moving with a smaller velocity afterwards. Simply because now we have both objects moving at the same speed. This person slowed down. They were moving at 2.3. Now they're moving at 2.1. This one sped up. It was moving at 1.5. Now it's moving at 2.1. This one lost momentum. This acquired momentum. But when we're all said and done, the total change of momentum is 0. That's how we used that law to be able to determine what that initial speed was. I am not going to do this problem with you. It's much more complicated, much more involved. I wanted to give you some time to be able to work on your homework. You should hopefully have at least a half an hour of time for you to be able to work on these problems. These are the problems that I want you to be able to do now. There are a lot of them, so get going on them. Practice D, 1, 2, 3, 4, section review 3, and then review 15, 16, 17, 23. Those are in section 6.2. I will place this video on Edmodo if you want to watch that again tonight. Good luck, guys and girls. We will see you on Tuesday. Go Bucks. As I promised, I'm going to stop the video with this up here. So now you may go Bucks.